this episode, we look at the parts of resilience that keep systems powered, keep data available, and make recovery possible after something goes wrong. It is easy to think of resilience only as a big disaster recovery plan, but many failures begin with ordinary problems. A power outage, a failed power supply, a damaged storage device, a corrupted file, a deleted database table, a ransomware attack, or a backup that does not restore can interrupt the business just as surely as a major disaster. Power and data protection work together because systems cannot run without electricity, and operations cannot continue without trusted data. Backups sound simple, but they are only valuable when they are complete, protected, current enough, and tested. Immutability adds another layer by making backup data harder to change or destroy. Restoration testing proves that recovery is more than a hopeful assumption. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at CyberAuthor.me in the Bare Metal Study Guide series. Power resilience begins with the reality that computing systems depend on stable electricity. A sudden outage can shut down servers, network devices, storage systems, security tools, and user workstations. A brief power drop can interrupt a transaction, corrupt data, or force systems to restart unexpectedly. A power surge can damage equipment. A longer outage can stop building access systems, cooling, communications, and monitoring. Security teams care about power because availability is one of the core goals of protecting information systems. If a critical service is offline, people may not care that confidentiality and integrity controls are still beautifully documented. The service is not available when it is needed. Good power planning tries to reduce the chance that one electrical problem becomes a full operational outage. That planning includes short-term battery support, redundant components, longer-term generation, surge protection, maintenance, and realistic testing under expected loads. An uninterruptible power supply, UPS, provides temporary power when normal power is interrupted or unstable. You can picture a UPS as a short-term bridge. It gives systems enough time to keep running through brief outages or to shut down safely during longer ones. For small equipment, a UPS may protect a workstation, network switch, or security appliance. In larger environments, UPS systems may support server rooms, storage arrays, network equipment, or data center infrastructure. The purpose is not always to keep everything running for hours. Often, the purpose is to prevent sudden loss of power from causing data corruption, hardware stress, or uncontrolled shutdowns. AUPS also gives generators time to start when generators are part of the design. For Security Plus, remember that a UPS is about short-term continuity and graceful transition during power problems. Redundant power supplies help protect individual systems from the failure of one power component. Many servers, storage devices, and network appliances can be built with more than one power supply. If one power supply fails, the other can continue supporting the device. In stronger designs, those power supplies may connect to different power circuits so that a single failed circuit does not take down the entire device. Redundancy is valuable because hardware components fail over time. A power supply can burn out, a cable can loosen, a breaker can trip, or a power strip can fail. Without redundancy, one small component may stop a critical system. With redundancy, the failed component can often be replaced while the device keeps running. This does not mean the system is invincible. Redundant power supplies need monitoring, maintenance, and proper connection. If both supplies are plugged into the same failed source, the benefit is much weaker. Generators support longer outages by producing electricity when utility power is unavailable. A generator is not the same kind of control as a UPS. The UPS usually covers the immediate gap, while the generator can provide power for a longer period if fuel, maintenance, and capacity are handled correctly. Generator planning includes knowing what equipment the generator supports, how quickly it starts, how much load it can carry, how long fuel will last, and how fuel will be replenished during a widespread emergency. A generator that works during a calm test may not help much if it has not been maintained, if fuel contracts fail, or if the load is larger than expected. Generators also need safe installation, ventilation, transfer equipment, and testing. They are part of resilience, but they are not magic. They have limits, and those limits need to be understood before an outage occurs. Surge protection guards equipment against voltage spikes. A surge can come from lightning, utility problems, large equipment switching on or off, faulty wiring, or other electrical disturbances. Even when power does not fully go out, unstable electricity can damage sensitive electronics or shorten equipment life. Surge protectors and power conditioning equipment help absorb or manage these spikes before they reach systems. In a home office, this may be as simple as using a quality surge protector for a computer and network equipment. In a business environment, surge protection may be part of building electrical design, data center power distribution, or rack-level protection. This control is easy to overlook because it is not as dramatic as a generator or recovery site. Still, protecting against power quality problems helps preserve availability and hardware reliability. A resilience strategy should consider not only whether electricity exists, but also whether it is stable enough for the equipment. Storage resilience focuses on keeping data available and protected when storage components fail. A storage device can fail physically, a file system can become corrupted, a controller can fail, or a cloud storage service can experience an outage. Organizations often use redundant storage designs, so one failed disk or component does not immediately cause data loss. They may also replicate data to another system, another site, or another region. Storage resilience can support availability, but it should not be confused with backups. Redundant storage may keep a system running when a disk fails, but it may also immediately replicate a bad change, accidental deletion, or ransomware encrypted file. If the main copy becomes damaged and the damage is replicated, redundancy may preserve the problem very efficiently. That is why storage resilience and backups are related but different. Storage resilience helps systems keep operating. Backups help you recover earlier trusted versions. Backups are copies of data made so the organization can restore information after loss, corruption, deletion, damage, or attack. A backup might protect files, databases, virtual machines, application data, configurations, logs, or entire systems. The value of a backup depends on what it includes, how often it is created, where it is stored, how it is protected, and whether it can be restored in time. A backup that misses critical data may give false confidence. A backup stored beside the system it protects may be lost in the same incident. A backup that attackers can delete may not survive ransomware. A backup that takes too long to restore may not meet the business need. You should treat backups as part of recovery capability, not just as stored copies. The organization is not really protecting itself by saying backups exist. It is protecting itself when those backups can support a real recovery. Different backup approaches balance time, storage space, and recovery needs. A full backup copies everything in the selected scope. It can be straightforward to restore, but it may take more time and storage. An incremental backup captures changes since the last backup of any type, which can save space and time during backup creation, but may require multiple backup pieces during restoration. A differential backup captures changes since the last full backup, which can make restoration simpler than long chains of incremental backups, while still using less space than repeated full backups. You do not need to become buried in backup mechanics to understand the security point. The backup method should match the recovery need. If a system changes frequently and downtime is costly, backup frequency and restoration speed matter. If data changes slowly, a less aggressive schedule may be acceptable. Backup design is always a trade-off between risk, cost, time, and operational importance. Backup location matters because a backup can be lost in the same event that damages the primary system. If the only backup is connected to the same network, in the same building, and accessible with the same administrator credentials, the organization may be exposed to fire, theft, flood, ransomware, insider misuse, or accidental deletion. Stronger strategies often include more than one backup copy, with at least one copy separated from the primary environment. That separation may be physical, logical, administrative, or cloud-based, depending on the design. Offline backups are disconnected when not in use. Off-site backups are stored away from the primary location. Cloud backups may provide geographic resilience, but they still need strong identity controls and protection against deletion or account compromise. The main idea is that backup copies should not all fail for the same reason. Separation gives the organization another chance when the primary environment is damaged. Immutability means that backup data cannot be changed or deleted for a defined period, even by accounts that might normally have broad access. Immutable backups are especially valuable in ransomware scenarios because attackers often try to destroy or encrypt backups before demanding payment. If backup copies are mutable, meaning they can be changed, deleted, or overwritten, an attacker with enough access may remove the organization's recovery path. Immutability helps protect that recovery path by locking backup data against alteration during the retention period. This does not mean every immutable backup is automatically safe from every possible problem. The settings must be correct, the retention period must make sense, access must be controlled, and the backup platform itself must be protected. Still, immutability is a powerful concept because it changes the attacker's job. Instead of simply deleting recovery copies, the attacker must overcome protections designed to preserve them. Restoration testing proves whether backups can actually be used. This is one of the most important ideas in the entire topic. A backup that has never been restored is an unanswered question. It may be incomplete, corrupted, encrypted with a lost key, missing dependencies, too old, too slow to retrieve, or incompatible with the current environment. A restoration test takes backup data and confirms that it can be recovered into a usable form. That may involve restoring files, applications, databases, virtual systems, configurations, or full services in a safe test environment. The goal is to find problems before an emergency. A failed test is not embarrassing if it leads to fixing the process. A failed real recovery during an outage is much worse. Restoration testing turns backup from a claim into evidence. It shows whether the organization can recover what it thinks it can recover. Restoration testing should also check whether recovered data is trustworthy and usable. A file that restores but contains old information may not meet the business need. A database that restores but lacks required transaction records may create serious problems. An application server that comes back online but cannot connect to identity services, storage, or network dependencies may not be truly recovered. Recovery is not just copying data back into place. It is restoring a working capability. Testing should ask whether users can access what they need, whether permissions remain appropriate, whether security monitoring still works, whether encryption keys are available, and whether the restored service behaves correctly. This broader view matters because real operations depend on relationships between systems. A backup of one server may not be enough if the application also depends on databases, certificates, configuration files, service accounts, and network rules. Power, storage, backups, immutability, and restoration testing all connect during real incidents. Imagine ransomware affects a file server. Redundant storage may keep the hardware running, but it will not help if the files have been encrypted by the attacker. AUPS may keep systems online during a short power interruption, but it will not restore deleted data. A generator may keep the data center powered, but it will not protect a backup that was never created. Immutable backups may preserve clean recovery points, but the organization still needs to restore them successfully. Restoration testing may reveal that recovery takes longer than the business expected, which may lead to better backup design or more resilient storage. Each control has a role. None replaces all the others. Resilience comes from combining controls so the organization has power, protected data, recoverable copies, and tested procedures. For security plus questions, pay attention to the problem in the wording. If the scenario describes short-term power loss and a need for graceful shutdown or a bridge to generator power, think UPS. If it describes a device continuing to operate after one internal power component fails, think redundant power supplies. If it describes long-term power during a utility outage, think generators. If it describes voltage spikes, think surge protection. If it describes recovery from deleted, corrupted, encrypted, or lost data, think backups. If it describes preventing backups from being altered or deleted during a retention period, think immutability. If it asks how to know whether backups will work, think restoration testing. The exam may present several controls that all sound helpful. Your job is to match the control to the specific failure or recovery need being described. The larger lesson is that resilience has to be proven before the emergency. Power controls keep systems running or help them shut down safely. Storage resilience reduces the impact of component failures. Backups provide a way to recover data after loss, corruption, or attack. Immutable backups make recovery copies harder to destroy. Restoration testing confirms that recovery is possible in practice, not just promised in a policy. A backup is only useful if it contains the right data, survives the incident, can be accessed by authorized people, and can be restored in time to support the business. That is the heart of this topic. The goal is not to collect resilience buzzwords. The goal is to understand how each control helps the organization continue operating, recover trusted data, and avoid discovering too late that its safety net was never strong enough.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.